Hello, everybody. Can you hear me? Can you all hear me?
Yes.
Can people hear me?
Yes, we can hear you.
Can you hear me, everybody?
Yes, sir.
Oh, wonderful. All right, we'll start in a moment. This is going to be a little, well, it's going to be like you're all virtual instead. So many of you have done virtual already. I'll just have some announcements. Basically, we're just going to be doing this for the next 2 weeks. I'll be online during my office hours as scheduled before. And for those of you in my labs, we'll have a pre-lab lecture at 1:30 each day, just to go over the sheet, the take-home sheet. And believe it or not, the take-home sheet is pretty good because it's great on the hydrogen spectrum. The only thing you won't be able to see are the little pictures of the thing through the, how do I put it? You won't be able to see the spectrum through the lenses or whatever else when you're looking at the light itself, and that's why I provided the video. So before we have the lab time, for those of you in my lab, just watch those videos before, and then what we'll do is I'll just go over the sheet and help you understand how to do the calculations, and that'll be it for the lab, and that'll solve the problem for some of you in quarantine anyway. So hopefully you all remain healthy. Are there any questions before we start the lecture portion? I'm just going to continue where I left off. Any questions, anyone? Anybody have any questions?
So we just complete the dry lab for Friday?
Yeah, and that'll serve as a quiz, and you just email it to me. But also for those of you in my lab, it'll be the lab you're doing this week. But Dr. Gerhardt is going to be preparing 2 pre-labs for the other labs you were going to do, the color lab and the other one. And basically, you'll see the pre-labs next week, and then when you come back, you'll do them quickly in the laboratory in person. He wants to do those in person. So and the structure lab that I had kind of sent out to everybody, you could just do it for practice later. But basically, that's just going to be the college already has one that's similar to that. But if you want to purchase the kits, by all means do so. Otherwise, the college does have kits to do those in person to make the structures in a few weeks when we have that models lab. I believe it's the second or third lab to the end of the semester. So are there any questions?
I have one.
Sure.
Do you know when we're gonna get our exam grades back?
Yes, they've all been graded. I've got them in the system. I was going to put them in tomorrow. I was just waiting to hear regarding those that missed the test as to when they were going to do a makeup. But probably the way it's working out this way is they'll just have to take a makeup when I get back. It'll be a totally different test. So basically, I will be posting them tomorrow. Right now, I'm in Red Springs because I went back to see my grandkids and other things here, and I'm kind of stuck here, but I'm coming back to Clinton today to pick up some stuff and basically be back here. But I've got lots of other stuff to basically to grade all the lab exams from last week, and so everything will be just as normal. I just won't be using my office. Does that answer your question?
Yes, sir. Thank you.
Okay, any other questions? Anyone else have any questions?
Were the grades good?
Sorry?
Were the grades good?
Well, basically, those that did the homework and everything else did okay, and some grades improved, other grades didn't. But again, this is 1 out of 4 tests, and then we have the final. So, and I'm hoping that if you did better on the first test and not so well on the second, that I'll be able to minimize the second score. So that'll help you. But basically what I've seen is there are a lot of you students who are just using the PowerPoints to study. And I just want to reinforce the most important thing to do is read the textbook see everything in context and see my PowerPoints as being highlighting the important details, and then go back to the textbook, work the problems within the text, and then work some problems for each little section at the back of the chapter. Basically, if you open up the textbook, you'll see the text where you do the reading, and there's sample problems within there with some practice problems. Just do them along as you go through the reading, and then at the end, there's a set of problems for each section. So do at least half of them just to practice again so you understand the material, and then email me a question if you have questions, and use my office hours, whatever else, and I'll be online most of the time when I'm here anyway, so you can chat with me if you have any questions regarding that too. So the key thing again, basically what I found, and this has been the case all along, it's very hard to get students to do the reading first, because I even had students in Iraq that didn't want to buy the textbook, that just studied from the PowerPoints, and that's not really adequate. It doesn't really work to just study from the PowerPoints because they're just highlights and such, but at least you have the advantage of my lectures. So all I can say is just plot along, work as many homework problems as you can. Now the other thing regarding Hein, that Intro to Chemistry PDF I gave you, we're now in chapter 10. The introductory stuff for chapter 5 is in chapter 10. So if you need some background from your high school chemistry, or you don't remember enough, or you didn't take it, that's the one to read first, and then work some problems in there, and then read our textbook. And as we go through the rest of the semester, if you take my advice, please, and do that, you'll be able to accomplish a lot. And those that you bought Mastering Chemistry, there's all sorts of little tools and other things online that you can practice with or whatever else. But right now, because I don't know how to use the program, that is just auxiliary for now for this semester. But next semester I will be probably requiring it and having it be more involved in the curriculum, just to help students that want to make the effort to do it. But this semester I just didn't want to force everybody to pay for it. That was just my choice. Does that address any concerns anybody has? Any other questions regarding that?
Can you tell us what the average test score of the test was?
I don't remember it offhand. The way the curve was instead of the curve was, say, 15 points like before, and basically the top score after the 15 points was 90. And then it went down from there, but we had a bunch of A's, a bunch of B's, a bunch of C's and D's, and then F's. But right now I don't have I don't remember the average. My apologies.
When do we get our test grades back?
Well, as I said, I'm gonna post them tomorrow. They'll be in Brightspace tomorrow in the grade place, so they'll be posted tomorrow.
Okay, thanks.
Any other questions before I start the lecture? Okay, well, let's just plot along. We got 21 people online, and please stay online so I can call on you to see how everyone is doing. Just please make the effort please make the effort to be involved in the discussion, and I'll try my best to have things be clear for you regarding it. And so what I'm going to do first is kind of review a little bit of what is done with the energy aspect of light, talk about the nature of the quantum numbers, and then we'll go through the quantum numbers and talk about how you use the periodic table to kind of figure out what fills up the typical atom, whether it be iron or uranium or other atoms like that. So basically, let me go through the process now with you again. I'll have some overlap regarding what I did before. So I'm going to set up the slideshow now and then go to the thing and share the screen. We should be stable because my internet is very good here in my house. So everything should be stable there. Can everybody see the screen?
Yes, sir.
Okay, wonderful. Okay, so let's get going with this. All right, very good. So now the key thing to understand about Bohr's atom is essentially you start with, oops. You start with the center here, which is the nucleus, and then you have this first level, which is like the barrier, the onion. So keep in mind the onion example that I described to you before. And I hope that all of you took my advice, particularly those of you at home, cut an onion in half, and then you'll see what I'm talking about, because atoms are essentially just like that. That basically you have just a hydrogen atom, and basically you have the one electron going around the hydrogen atom. So basically the key thing is to understand the nature of the hydrogen atom is the electron goes around in a series of spheres, depending on how much energy that individual electron has. And one thing Bohr kind of thinks is that electrons can only have specific quantized energy levels. In other words, the first energy level might be a number like 10, and then the second might be 20. So it goes from 10 up to 20. If you provide more energy to the 10 one, eventually you'll just get faster and faster in that same orbit, and then it'll bounce up to the 20 to get to the higher one, so it has more room to go around. It's almost like it's got more volume, and so it expands the probabilities of electron being in a certain area. And light is emitted as energy moves from one energy level to a lower energy level. And the way things are excited is either with heat, with radiation, or other kinds of things like that, where the energy is absorbed first by the atom, like an explosion, like in fireworks, and then the energy is given off by giving off color as you go through it. And that's the value of this lab that I'm asking everybody to do, even if you have Dr. Gerhardt's lab this week, because basically the atomic spectrum lab really helps us understand the nature of how the light is first given off when electricity goes through it, because that's exciting all the electrons to get them to go to higher orbits, and then they want to go back down to the lower ones again, and so they dissipate energy, giving off just like, for example, if you've got a pot on a stove and you heat it up on the stove and then turn it off, that pot will cool down over a period of time, and that's the energy going off again. Well, in this case, if you excite electrons around an atom, they'll jump up and then they'll jump back down again and give off color at a certain place. So basically that energy difference is related to this formula here. So if you have the formula here where this is the constant, and don't worry about where the atomic physicists got that constant. They got it from experimental values. But basically the neatest thing about this that I enjoy is the fact that it's so orderly and makes sense even for freshman chemistry students or even high school students once you get into it. Because one of the things I always loved when I was growing up was going to see fireworks on July 4th and other times, whether it be in my small town like Clinton or other places, because my town only had like a population of 6,000, but we had fireworks at the high school also when I was younger. So in some respects, fireworks is a wonderful example of seeing all sorts of color from energy provided from the burning and the explosion, and then the light is given off as the electrons want to go back to their lower levels again. And that's related to the quantum numbers or the shells, 1, 2, 3, 4, etc. And again, the Rydberg constant, they got that from experimental experiments on that. So again, the dropping of the energy gives off light as it goes down from the higher level, but it had to get up to this level in the first place. And this is by absorbing light or heat, okay? And then it gives off light as it goes off. Essentially, it gives off light, and this is a lambda giving off light as it goes down.
Can you go back one slide for a second?
Sure. What question do you have on this one?
About the equation.
Well,
I'm just
basically,
wondering.
that's the energy at a certain level. For example, if you've got a satellite going around the Earth, what has more energy? Something if it's 22,000 miles high, or something if it's 500 miles high. What has more energy in it?
The one that's higher?
Yeah, right. Because it's going in a lot more area and it's going faster, and that's what geosynchronous orbit is about. And the way it got that extra energy was by the rocket that got it up to that higher level. As it dissipates energy, orbits will decay, and then eventually satellites will come back to Earth again. Well, in some respects, the atom's the same way, that eventually it'll decay and it'll bounce down and it'll give off light as it comes down. And that's essentially the colors that you see in the slides. So this is the energy of the light that's given off when it drops. And I'll explain that in a few slides, like the things, and that's the value of this lab. Did that answer your question? Did that answer your question?
Yeah, it did.
Okay, so let's just move on. But basically the energy given off, there's two different changes of energy. If you see the top one, there's not much energy change going from the ball at that level to that level. And that's all about the potential energy difference, because you got the mass, the gravity times the height. And then back down here, you've got a bigger energy change because the height change is different. Well, in some respects, the atom works the same way when you do that. And this is the
Can you
hydrogen.
go back really fast?
Sure.
And what's the equation for the kinetic energy and the potential energy?
Okay, kinetic energy is equal to 1/2 the mass times the velocity squared. That's related to the energy that's, for example, if you drop a ball from holding it high in the sky, and then it's going a certain speed when it reaches the bottom. That's the kinetic energy that's given off. It's changed from potential energy to kinetic energy. And we'll get that into more depth later in chapter 9 when we get to that chapter. But unfortunately, the way this book orders things, when it talks about electrical energy and light energy, it introduces that first, but the whole concept of potential energy is better covered in chapter 9, which is my normal order of teaching it. But Presbyterian College, the chemistry faculty, does it the other way, which is fine with me. I'm just adjusting, but I'm just saying that that's where we're going with it. And for those of you that say, trust me, we're coming along, the only reason I do that is because many of you are thinking ahead, which is fabulous. And basically the key thing is my words, when I say that, is basically this will be explained in future things. Right now, the scientists and chemists came to understood things by coming to the explanation about why something functioned later. Based on research and based on doing experiments, they were able to kind of see the big picture first and then get into the fine detail. Well, essentially what I'm doing now is kind of introducing you to the big picture. And the best way to represent that is just all the colors you see with a fireworks display. Okay?
What is the equation for potential energy?
That's mgh. Potential energy equals m times gravity, that's the mass, times the height. And that's why we have the steps here that kind of illustrate that. But when you're talking about potential energy and kinetic energy around an electron, around an atom, the kinetic energy is related to the next slide with the previous slide, which is this one here. This is the kinetic energy that's involved in the transition between the one level and the second one when the energy is given off. That is also kinetic energy because it's energy of motion.
Is the photon the light that comes off?
Yes, yeah, and the way it's represented, it could be either as a particle, a photon, or as a wave. But for the context of this thing, it's a little easier to understand if like it's a thing in orbit around the Earth, so to speak, because it's just a little easier to understand instead of seeing it as a wave, sort of that. But the electron is a particle, so that's the key thing. The electron moves from one place to the other, but a photon is energy that's given off by that by that electron when it has a transition. Okay. All right, well, let me move on here with the next one, the next slide. But basically here, quick question for you. How did these electrons, this is one electron, how did they get up to the higher levels? How did it get up to this level 7, 6, 7, 6, 5, etc.? How did it get up to that higher level in the first place?
By absorbing light.
Yeah, by absorbing all sorts of energy. There's heat energy, there's all sorts of energy in the thing. So basically, there's light anywhere, it will get absorbed, and then when it comes down again, and if some of you already saw those little videos about the spectrum, basically the energy comes from the electrical current that comes through the lamp, which gives off the certain colors. And for example, I've got LED lights behind me, or you might have a fluorescent light in your dorm or in your home. Okay, the fluorescent light essentially, the electricity goes in it and lights it up, but then the color is given off because these electrons go back to their lower levels. And these are the colors that are involved that we can see, and it's in the Balmer series, and that's what that little lab is going to be about, is studying the Balmer series of electron transitions within the hydrogen atom. And the energy of the photon, the change of the energy here, basically you got the change of the energy associated with this. That is the difference between the final energy and the initial energy. That's the change in energy. And then you plug the equations together and you can get the, you plug the equations together where you have the final, and then you have the initial related to both of them. You plug them in there and you get that one. And that's the value of the lab, because you're going to be calculating those transitions, the change in energy with that hydrogen lab that I showed you that I've assigned for you to work on this week. And
where did all of those equations come from?
well, they came from the scientists who figured them out. And basically it's related to the mathematics that's used in helping people understand the wave functions and other things, like Schrodinger and others who came up with the calculus and the differential equations that went into these wave functions and such. So basically they were derived experimentally as a way to explain why the colors came off. So they were able to determine what that is. And that's the value of the scientific method, is you come up first with a hypothesis, and then you figure out and come up with theories which explain it through experiments. And that's how they got it, through experiments. And that's the nature of a lot of neat inventions in chemistry and in physics, was that they saw a phenomenon first and started asking questions why, and then they came up with the mathematical expressions which showed that it worked. And these mathematical expressions, that was over a series of years of research where they came to all these different conclusions. And people like Niels Bohr, Max Planck, de Broglie, and all the others, all the other people that are talked about in the beginning of chapter 5, they did all those investigations, and that's why many of them won Nobel Prizes. Okay, so here you got the transition from 2 to 1 here, you plug the values in there, or 3 to 1, you can determine exactly how much energy there is for each. And basically the various series of them, the Lyman ones are ultraviolet in the spectrum region, and then you have visible and ultraviolet under the Balmer, and then the Passion and Bracket are infrared radiation give off. And then there's some examples of calculating the wavelength and photon emitted when it drops from n equals 5 down to 3. Well, you plug the values in there, and again, pardon my, let me erase what's on the slide. Maybe, hopefully it'll let me. Oh, no, I can't. It's already stuck on the slide. But the big thing is here, you plug it into the equation, you put the equation down, and that's what that lab you're going to be working on this week does. You're going to be putting the numbers in there using the constant and calculate first the energy related to it, the change in energy, and then using the other thing, rearrange it to form the wavelength of the light. And this is the wavelength of the light after you rearrange it, and then you plug the values into that, and that gives canceling out the things. And this one is 1280 nanometers, which is not in the visible region, because the visible region goes from 400 to 700 nanometers. This is visible. So this is in the other one there. Now, why is energy quantized? Again, this is the Broglie reason that electron is both a particle and a wave, and basically put the wave around it there. And so he came up with this mathematical relationship. And he did this with using mathematics and a whole lot of experiments to come up with that. And basically, the only thing I'm going to ask you to do is just see the equation there and see how it works. Other than that, we're not really going to get much into the de Broglie aspect of wave particle at this stage in General Chemistry 1. It's kind of like extra detail you don't really need to understand it. And then a bunch of examples of ping pong balls, and wavelengths on stuff like ping pong balls to me never made any sense, because the wavelength is incredibly small. And so it's kind of, and look how small this wavelength is, 10 to the minus 23rd. And it's like, what's the point? So in a way, the fact that this teacher likes to put that in there, and I believe there's an example in your textbook too. It's interesting for mathematicians, but for General Chemistry 1 students, who cares? So I just want you to understand the big picture here when we're talking about these things. And then they got the example of a laser and how energy is used to essentially by electricity and a lamp to kind of focus energy into a beam, and then it reinforces one another. It's a coherent thing, the waves reinforce one another. And electron microscope takes pictures of atoms. Now, Schrodinger wrote an equation that described both the particle and the wave nature of the electron. And when electrons repel each other, the wave function was in there. And basically, again, what I referred you to was this is like a spatial representation of it, a special representation that can be made three-dimensional. And if you see, doesn't that look like an onion? When you cut an onion, doesn't that kind of look like an onion with the different levels? So that's kind of like a picture of the hydrogen atom, with this being in the center. This is the center, and then the different levels out from it. And you can kind of see it as a sphere. And the Schrodinger equation can only be solved exactly for the hydrogen atom, and it's only approximated for stuff like sodium atoms and uranium and other ones. So in some respects, the math is way too complicated to explain the nature of the spectrum from, say, mercury, a mercury lamp, which is a lot more complicated. Now, the quantum numbers, and what we're going to do now is use the whole concept of quantum numbers that we talked about before. The principal quantum number is n is equal to n.
Dr. Douglas,
Sorry,
will you
yes.
go back so I could take a picture? So I could take a picture of the.
Well, this will
slide?
be in the Zoom thing if you want to, where, this? You want to
Yes, sir.
take a picture? You're welcome to watch this Zoom again if you like.
I have a picture of it. Thank you.
Okay, good. All right, so let's go. What we're going to do now is talk about the quantum numbers. And again, if you look at a periodic table, it looks like this. Okay, and you've got hydrogen up here, hydrogen in the box up there. This is number 1, then 2, 3, 4, 5, 6, 7, going all the way down. And essentially, this has to do with the shell for the outer electrons in those different groups or rows. So essentially, when you have that shell there, that is what that is what the principal quantum number is essentially talking about, is essentially that shell. Okay, so let's first talk about that. And that's the distance of the electrons from the nucleus. Just like you start the nucleus here and you've got 1 there, that's the first one. This is n equals 1, n equals 2, n equals 3 going out. And as the nucleus gets bigger with more and more things, like say, for example, a sodium atom, essentially you will have more electrons going around it, because if you look at the periodic table, you'll see that sodium has a certain number of electrons, many more than the hydrogen atom does. Okay, so they're going to be in bigger shells. They need more room to travel, and so they'll be in bigger shells as they go around. So these are described as 1s, 2s, and 3s. And I like to see the s as being kind of representing a sphere. Okay, in other words, it's, if you were to peel that onion and peel off 1 layer at a time, you'll find the little core, and then you'll get the other ones coming out from that as it goes out from the center. So if you got a uranium atom, that's one of the biggest atoms there is. And of course, it's a very heavy metal when you're talking about uranium. And that's n equals 1, n equals 2, n equals 3. And what we're talking about there is a sphere related to it. And this here is a representation of n equals 1. And what is the green area there referring to? Before I go into it, this is a sort of a little verbal quiz. What does the green area refer to that? And just remember, there's this 1 electron going around. What do you think the green area or the fog area around it kind of represents? Any volunteers? What does that green area kind of represent?
Does it represent the electron cloud?
Sure. It's like where that electron might go around. Like say, for example, you have a baseball stadium and you put a baseball in the middle of the pitcher's mound. Where that electron going around the center can go around and fill the whole baseball stadium. And that's the nature of the atom, is it's mostly empty space with the electrons going around it. But that cloud is the probabilities of where that electron might show up at a certain time. And because they repel each other, they can almost be viewed as solid, because they will repel each other. And if you got different atoms, they'll naturally repel each other also, unless there's some charge associated with that. But it's not really solid, but it is. And there was some neat Star Trek Next Generation episodes where people were out of phase and kind of running through walls and other things like that, that sort of represent the fact that there's empty space, because when they were sliding out of space, they would be able to run through the walls because they were mostly empty space anyway, and they're slightly out of phase, they could get through the walls. But they neglect to mention in those silly TV shows that basically there's going to be a problem with the floor. They'd fall through the floor too. So it's just funny to think about. Any questions on this? Okay, let's move on.
I
What's
have
the
a question.
Sure.
Well, we were talking about Schrodinger's wave equation, we never actually had an equation.
Well, because it uses partial differential equations. That's explained much more in physical chemistry, and I think it's a great question. But that is for chemistry majors that will learn in physical chemistry, or those that take it in physics, and that is the fine details. What I'm trying to do is teach you about the forest right now. So don't think I'm dismissing you. You're right, there is an equation, but for you to explain it, for you to understand it, if you haven't had calculus and even advanced calculus, one of the funnest classes I took as a senior in college myself was quantum chemistry, and I really had a great time studying it. But I understood it at that point because I understood all the foundational material that I'm teaching you right now. So I'm not dismissing you. You're thinking very much ahead. So right now, I just like you to see it as a series of clouds. Does that sort of make sense?
Yeah.
Question.
Sure.
Does the green part have a name, or is it just?
Well, like this one, this is n equals 1. This is the 1s orbital. And we'll show you the other orbitals as we move through the slides. So you'll see some more in the future. So just hang in there, and I'll be describing. Well, let me look at it this way. The first one, when you have n equals 1, the next quantum number is considered L, and this is representing the shape of the orbital. And as you get bigger, the first one where L equals 0, it's a sphere. Where L equals 1, it's like a dumbbell. But it's in 3 dimensions. So the orbital looks like this. Okay, but you have 3 of them. You have one like that, one behind, and then one going up and then back down below. So there's 3 possible orbitals in that, but with a dumbbell shape. And that's how electrons go around that. And I'll move on so I could show you the better pictures that are in the that are in these slides coming forward. So basically, we'll move to the next one. The key thing is, sorry, yes?
I thought the dumbbell was only 1 orbital, not 3.
Well, there's 1 orbital, and there are 3 different orientations for it. So there are 3 orbitals where you have n equals, where you have L equals 1, and I'll explain that in a little bit. And that's kind of what I showed you in the classroom, in that little in the cabinet where it had representations of them. But these later slides kind of represent it pretty well. So you'll see what I'm referring to in a minute. Okay. But right now we're just talking about here, like this is 1, this is 2, this is 3, this is 4. As you go out, the radial possibilities, the distance from the nucleus, these areas where you have the higher probabilities, that would be where the thing is the most dark. So these bigger things with the circles around that would be like the layers of the onion, and these can represent the shells, where you have the previous slide. Let me show you the previous slide. This would be like the 1s, 2s, and 3s. But if you wanted, you could take this 2s thing and put it inside there, and you could put the 1s inside there. And in the center of this is a nucleus. Right here is a nucleus. The nucleus inside this. So it's like a 3-dimensional structure. And this is what the S ones look like. But these are just other representations of this, and the probability where the largest thing, that's the darker green in that color. Well, the L, this is the angular quantum number, and this is the essentially the shape of the orbital. of the orbital, and that's where it's the angle, okay? And for given value of L equals 0, 1, 2, 3, 4, all the way up to n minus 1. So if you have n equals 5, what are the possible values for L if you have n equals 5, folks?
4.
Yeah, it could be 0, 1, 2, 3, or 4. So it'd be the s orbital and then the other ones below. And when you get up to that fifth row on the periodic table, okay, that fifth row, there's an awful lot of elements along that fifth row. And what's happening there is those are filling up the orbitals underneath. And and that'll become clear as we move through the slides. But for n equals 1, L equals 0. And this is the sphere that I was referring to before, where L equals 0. When L equals, where L equals 0 or 1, okay, you have the sphere first. This is the sphere. And then you have the sphere and the dumbbell. And as I show you on this slide, this is what the dumbbell looks like. There's three possibilities. One looks like this, and another would look like going back behind and then in front. All combined together make like a bigger area of two. And the key thing is the reason the electrons go in that thing is when it's in a spherical shape, the electrons will repel each other, so they got to go in other orbits where they'll come out and go in and come out and go in again. And that's the nature of why you got these complicated spherical shapes outside of them. So I'm going to erase the slide again to do with this, okay? And so the L equals 0 is the s orbital, the L equals 1 is the p orbital, and then L equals 2 is a d orbital, and the d orbital looks like this, where you have one like that and another like that. So the electron could go in all these different lobes as it travels around, and the d orbital looks like that. And there's a slide with all of those on it coming up in a couple of slides. But basically, these are the most important orbitals that we deal with in our class this semester. And then L equals 3 is the f orbital, and that has a more complicated shape. And it's the shape of the volume of space. The orbital is the shape of the volume of the space that electron occupies. So you have the s orbital that's a sphere, the p orbital, which is a dumbbell, looks like that, a d orbital that's a double dumbbell, oops, sorry, a double dumbbell, and then the f is more complicated. Okay, these are the s orbitals, okay? This is the sphere that I was showing you before. And the p orbitals look like that. Brandon, does that help you understand the p orbitals when they're shaped sort of like that?
Sort of.
Yeah, they're like in a three-dimensional structure that kind of go out from the center. Because there isn't enough space for these extra electrons to get shoved into these. They have a certain orbit that goes out past them. So the s orbital might be in this way, but there'll be a certain area outside the orbital that the p orbital can occupy. So the combination of all of them together enable all the electrons to fly by each other and not repel each other, but be in a cohesive unit surrounding the atom when you get bigger than the hydrogen alone. And this is what the d orbitals look like. And see the double dumbbell orientation, but then there's a special one there which kind of fills out the three-dimensional structure. And the key thing to remember is these are 3D structures, okay, that build up the shell as you go out from the center. So you start with the nucleus that's here, you end up with the s orbital coming out, and then as it gets higher to s equals 2, then you start getting the lobes that come in and out like that. in and out like that, etc. Then it goes to the next one. Then there are more complicated lobes that might look like this, and then this one going up like that outside of it. So basically they provide paths for those electrons to fill up the bigger space as you get bigger and bigger. And that's the nature of what these structures are as you move up. Okay, so ML, this is the magnetic quantum number, and this just represents the orientation or the direction that it's in. And basically for given value of L, ML will be this. So if N equals 1, L will equal 0, and ML will be equal to 0. But if N equals 2, L could equal 0 or 1, and so ML could be equal to -1, 0, and +1, which would represent this orbital, and then this one going back behind and in front. So the 3 p orbitals, these are the different directions that these all point. And this is the direction of the dumbbell being pushed. Like in the previous slide. Let me go back to the previous slide there. See here the direction. This would be like ML equals -1, ML equals 0, ML equals +1. Okay, so those are the 3 things. That's called the magnetic quantum number.
Wait, so what's the equation for the ML?
Well, the ML goes from -L up to +L. So if N equals 1, L would be equal 0, right? So the only possible value for ML would be 0. But if N equals 2, you can have the s orbital and the p orbital. And then with the ML, you'll have it be in the x direction. This would be in the y direction. This would be in the z direction, like I showed you before on these slides here. Like this one is on the x, or this is on the x-axis, right? This is on the y-axis, and this is the z-axis on a 3-dimensional structure. Does that make sense? Okay, so basically we just basically have the orientation there, and it's the orientation of the orbital in space. That's just the direction it's pointed, like an x-axis, on the x-axis for p orbital. Okay, or on the y-axis, or in the z-axis. And the d orbitals are a little bit more complicated because they go in multiple directions, but it could be like flat along the x and y, flat along the x and z, etc. Okay, so ML, there are 3 orientations there. You could have this, these are the 3 orientations there, and these are all the p orbitals.
Will you go back a slide for 2 seconds?
Sure.
So it does all the L orbital options. So like if it's L is equal to 2, it's -2, -1, 0, not just.
Yeah, because there's 5 orientations for them, and I'll show them in the next slides. Like here, there's 3 orientations for ML equals -1, 0, and +1. But when you get to the d orbitals, see with this is your question here, you have 5 possibilities, and there are 5 orientations there, and that's what they all look like. See, the 5 orientations in space. Does that make sense?
So how can you look at one of those graphs and know the M value? Like, I don't understand how you can like look at the graph.
Well, you can't. These are probabilities that are described mathematically, but it's a model that helps you understand how the electrons circulate around the atom when you're bigger, talking about an atom that's higher on the periodic table than hydrogen. For example, if you have sodium, and for those, some of you has a periodic table, where is sodium on the periodic table? What row is it on?
The third.
The third, okay, and where is it? It's in the first one, correct? So how many electrons are associated with it? What's its atomic number? What is the atomic number for sodium?
11.
11. So the electrons have to go around it, right?
So, it has 11 electrons? as
Yeah.
well?
And they start off from the S shell, which is the center one, and then you got the 2s one, which is bigger, and then you get into the 2p, and then the 3s one. So essentially, there's a combination of all, and each of these can have 2 electrons, can have 2 electrons in them. Okay, if you go back to the other slide, each of these orbitals can have 2 electrons, Okay, so there's 2 electrons associated with each one of them for a total of 6 electrons. Now, look on the periodic table. For those of you who have the periodic table, on the right-hand side, how many columns are on the right-hand side of the periodic table? Going down, how many columns?
7.
No. Going down the right-hand side, how many columns are there? There's 6, right? There's 2 on the left, and then there's 10 in the center, and then there's 6 on the right. Columns going down, not rows, columns. Okay, so the periodic table looks like this. You got the 2 columns here, then you got this big gap here, which has 10 in there, and then you have the 6 here. We have 6 of them there. These are filling the p orbitals. Here, these are for the d orbitals, and here these are for the s orbitals. So essentially, you have each of these orbitals filling electrons as you add them to it. That's called the Hofbauer adding up principle, which we'll talk about also next class. But basically, the representation of these is quite good when you see these structures there. And you have each of these having 2 electrons associated with them. And that would explain why there's 10 electrons in the transition metal area, the 10 different elements, because 1 electron is going in as the center gets more and more protons to thing. Now the last one is called the quantum number ms, and that is equal to +1/2 and -1/2. And this represents the spin, or which direction that electron moves in. So it can go in a north-south direction, or it could go in a south-north direction, the orbit around the center. So the one on the left is +1/2 things. So basically what this says is there's 2 electrons per orbital, and they both go in opposite directions. So all what I've been showing you is the orbitals that related to it. And the Schrodinger wave equation is just a mathematical wave equation, which essentially describes what is happening physically when you're talking about the electrons going around it. Okay. And so,
what is it adding 1/2 or subtracting 1/2 from?
well, it's just the last one of it. Say, for example, you have n equals 3, L equals 2, ML equals -1, and then MS equals -1/2. This is how 1 electron in an atom is described. So these are called, this is called the Pauli exclusion principle, which essentially this, when it has n, the shell is, the sphere is 3, the L is 2, like it's a d orbital. The ML would be +1, which is just one of the possible 5 ones, and the MS, and that's a description of 1 electron in that orbit. So basically, you put all the numbers together, and those are called quantum numbers related to them. And basically, we'll talk about the combination of all of them next time. But when you've got atoms associated with this, say, for example, you have an oven with a slit stream, and this is kind of how these were discovered with a magnet. The MS with one electron would go up, the other one would go down, and they would be detected in this. And this is kind of like the experiment that they used to determine the fact that electrons would go into different relationships between them. So the way the quantum numbers things, the existence and energy is described by its unique wave function, and those quantum numbers are illustrated by these letters, so to speak. And the Pauli exclusion principle basically says that no two electrons in an atom can have the same 4 quantum numbers. So basically what that means is that the electrons in an atom will not follow the same path as the other ones because they would naturally repel each other. They've got to have their own special path to go around. And so basically they're going to have things, just like I said before, you have an n equals 3 for one thing. The ML could be going from the L could be equal to 2. The ML could be equal to +2. And then the MS would be equal to +1/2. This describes one electron around that atom. So the N would be equal to 3. That's the shell it's in, like the onion. The L equals 2. That's the shape of the orbit. The ML equals -2. This is the orientation. Okay, this is the shape of the orbit. This is the shell. And this is whether it's going in the north-south direction or south-north direction. Okay, kind of going around the atom as it sinks. So those are essentially what's involved when you talk about the quantum numbers. And again, they give the example of a baseball stadium. Each seat is uniquely identified. Well, each atom can be uniquely identified in a sodium atom. So the sodium atom has 11 electrons. 11 electrons. And they fill up the orbitals are 1s2, 2s2, 2p6, 3s1. So if you add these all up, that equals 11. This is the electron configuration of sodium, electron configuration. And we'll get into electron configuration next time. But that's the nature of the sodium atom, that it has all these different shells that's filling up. When you've got the center that's the nucleus is very straightforward. Does that?
Electron configuration adds all 4 of the quantum numbers?
Sure, And I'll explain that with the next lecture. We're done for the day, it's 10:53, so hopefully it went all, did everybody like today's lecture? Did it go pretty well for everybody?
I was confused on the last couple ones that you explained, but I'm just gonna read it more over the PowerPoint.
Sure, but also read in the textbook too, please. And if you want an introduction for it, go to the Hein chapter 10.
Okay.
The Hein chapter 10 will introduce it to you. And there's better graphics in the book also that you can see them too. And it's all put in context.
Okay, thank you.
So use the PowerPoints to help you study the textbook, okay? So we're all done today. So thank you very much. And hopefully all of you feeling good. So bye for now.
Dr. Douglas?
Yes.
What's the chapter in our actual textbook?
Chapter 5.
Okay.
Okay? Have a good day. Have a good day, everybody. Bye. Thank you.